All right, welcome back to Lean Together 2025. And we're now going to be listening to Christian Merten tell us about formalizing the Bruhat-Tits tree in Lean.
Yeah, thanks. Yes, yes, I'll be talking about the Bruhat-Tits tree, and this is joint work with Judith Ludwig from Heidelberg University. And for those that don't know the Bruhat-Tits tree, let me give you some motivation of why this object is interesting. So let P2 be the set of real, positive, definite, symmetric 2x2 matrices. That's a nice set. It's an open subset of some vector space. And why is it a nice set, or why is it an interesting set? Because it has a group action, and it has a group action by GL2R. And GL2R acts transitively on this P2 by just sending a P to G times B, P times G transpose. And this action is transitive, and if you look at the identity, so P to be the identity, then the stabilizer is precisely the orthogonal matrices in GL2R. So the stabilizer at the identity of this action is O2, which is a compact subgroup of GL2R. So this P2 is just a quotient of GL2R by O2R. So this P2 is an example of a real symmetric space. And why do we care about this? Because it gives us some handle on understanding this group GL2R by letting it act on some nice space, in this case, even a Riemannian manifold. And so the question now is there an analog for this in the world of p-adic numbers, or in the p-adic world? And yes, there exists an analog of symmetric spaces, namely the buildings by Bruhat-Tits. And the Bruhat-Tits tree is just a special case of these buildings. And so, of course, already in the name tree and in the name building, you observe that this is somewhat different in nature from the real symmetric spaces, which are Riemannian manifolds. So this is really a combinatorial object. And so the goal of this formalization was to show that the following image is correct. Namely, this, I claim, is the Bruhat-Tits tree for the two adics for Q2. And it's just the most boring tree that you can imagine. It's a regular tree of fixed degree 3. Okay, but so the goal is the tree is a boring tree, and but to get there from some definition is, of course, the part of the goal of this formalization. So what are these points in here? These red dots. The red dots are the vertices. And what are the vertices? The vertices are lattices of in Q2. And so what's a lattice? And there has been a long discussion on what's a lattice and what should be a lattice. And eventually this discussion somehow ended by just having now a definition of a lattice. But of course, we already have different definitions of lattices, but let me give you the definition that we have. So that's the setup. R is a discrete variation ring, K is a field of K is its field of fractions, and V is a K vector space. And so if you don't know what these words are, then just pretend R is the two adic integers, K is the two adic rationals, and V is some K2. And then the basic building block is the notion of a lattice. So submodule M of V is a lattice if it's finally generated as an R submodule and its K-span is V. Right, so the standard example of this, if we just consider V to be K2, then R2 in K2 is a lattice, and we will refer to this as the standard lattice in the following. So, and of course, if we have a uniformizer of R, so any irreducible element of R, then the submodule var pi to the nr plus var pi to the mr is also a lattice. And somehow these are the only lattices up to some coordinate transformation of V2, of K2. Okay, so already here I'm being a bit abusive with my language, because the first thing the definition says a submodule is a lattice, and in the second example, I say this lattice is the standard lattice. I didn't say a lattice is. I said something is a lattice. And just to point out this difference more clearly, our definition is a submodule is a lattice. But I could have also said a lattice is a finitely generated submodule. And where the first thing is some propositional predicate on the type of all submodules, and the second thing is some new type. And of course, informally, this is only a matter of wording, but formally, we get two different definitions. And typically, we only want one of them. So let's fix the following setup. Take K to be a field, R a subring, and V a K-vector space. Then that's what is a lattice is, and what is now in MATLAB as submodule.isLattice. And it just says what I just said. It's finitely generated, and it spans the whole space over K. And typically, that's the object that you want to work with, and you want to develop as much API as possible in this setting, working with general submodules, and the predicate is lattice, and show this is lattice predicate has some nice stability properties. But if you want to formalize a tree that is built from these lattices, you also want a type. And so we also have a type that is a lattice, and that is a submodule together with this condition. Okay, so we have lattices, and I told you a little lie that these lattices are the vertices, but it's not really far from being the vertices. And for simplicity, we now just fix V to be K2. And namely the lattices, the vertices are not exactly the lattices, but some equivalence classes. And these equivalence classes are obtained from, we have an action of K, of the units of K, on the R lattices, just by a scalar multiplication. So we have this instance, and we then say two lattices are similar if they agree up to some non-zero unit scalar multiple. And which then reads as two lattices are similar if they exist some A and K times as a K unit, such that A times L is N. Okay, and the vertices are then the quotient by this relation is similar. There's a question in the chat by Kevin. Should that field be called M or to submodule? Yeah, it should be called to submodule, maybe. Maybe we even want a coercion to submodules. L.M, I agree, L.M is a bit hard to read. Especially if you have M.M and L.M and K.M, then yes. Okay, the vertices are thus just the quotient of lattices by this is similar relation. And now we have the vertices, but we want the edges. And for this, we need a little detour. Namely, we need some more input on lattices. And the most important result on this is the invariant factor theorem, invariant factor theorem. And I just give it to you. So let L and M be R lattices and var pi a uniformizer. Then there exists an R basis of M. There exists an R basis of L and integers n1 greater equal than n2, such that var pi n1 b1 and var pi n2 b2 is an R basis of M. So in some sense, we can twist the coordinate system in a way such that the M is just some uniformizer scalar multiple of L. And the pair of integers n1 and n2 only depends on L and M, not on the basis, nor on var pi. And this is really two parts, this existence and uniqueness part. And the uniqueness now gives us this well-defined signature on a pair of lattices that is n1, n2, and we'll use this to define some distance function on lattices to compare different lattices and to define when they are neighbors. Okay, so up to coordinate transformation, every lattice is of the form var pi nr plus var pi mr, r as I explained as in the example in the beginning. Okay, and of course we want to define something on vertices, not only on lattices. And for this, this is the easy corollary from the theorem. This difference n1 minus n2 only depends on the equivalence class of L and M with respect to scalar multiples. Of course, the signature itself, so the pair n1 and 2 depends on the equivalent on the choice on the representative, but the difference does not. And this corollary now, yeah, the proof of both of these relies on the Cartan decomposition, which is some decomposition of matrices of elements of GL2K, which was somehow formalized as some part 0 of the product. Okay, and now we can define the distance between vertices. What's the distance? Well, if we have two vertices, L and M, then the distance is just the difference, n1 minus n2, where n1 and n2 are, as in the theorem, or the corollary. So we have some notion of distances, and this distance function has some standard properties. So the distance of L and M is 0 if and only if L is M, and the distance is symmetric. And importantly, it's invariant under the action of GL2. So remember, our starting point was we want some object where GL2K acts on. And if we now define vertices to be neighbors or to have an edge, if and only if the distance is 1, then this distance is better preserved by the action of GL2K for this GL2K to act on this graph in a meaningful way. Okay, and here I want to make a little interlude on the proof of this last step. Because as you might imagine, if I go back to the theorem, the invariant factor theorem, this involves a basis of L and a basis of M, and quite some explicit data. And this sounds like it could be quite hard to state in Lean or quite painful to work with. And this essentially comes down to 3 different perspectives on lattices that we can take on. So the first observation is any lattice is free of rank 2. It's a submodule of some vector space over some fields, so it's torsion free and it's over a principal ideal domain and it's finitely generated. So it's free, so it has a basis. And so the most natural perspective, maybe mathematically, is we work with a 2-element R basis of M. So it's an R basis of this module M. If you come from the GL2K acts transitively on this space perspective, then you might take the perspective that a lattice is the span of the columns of some element of GL2K. And if you want to formalize this, then you might want to take the third perspective, namely it's the R span of a K basis of K2. And of course, the first and the third one are very similar. And informally, these would never be distinguished. But in formalization, this really made a difference. So just to give you an example, in the beginning, we had a lot of lemmas of this form. So this exists reproduced, and these lemmas still exist, but they're not used anymore. So if we have 2 lattices, then there exists a uniformizer, so a var pi that is irreducible, and a basis of M, a basis of L, and some indices, such that the ith entry of the basis of L is some multiple of the ith entry of the basis of M, such that the difference of the coefficients is precisely the distance. This is essentially the definition of the distance function. But you could, if you pay attention to the dot val, this already hints at possible issues with this lemma. Because it doesn't say anything about BLI, it only says something about BLI.val. And this lemma can't say more, because the terms BM and BL have different types. One of them is a basis of M, and one of them is a basis of L. So a priori, they can't be compared. The only way to compare them is to push them to K2, to the surrounding space. And so one way to solve this is to consider instead a basis of K2 that represents M and a basis of K2 that represents L, and relate these 2 bases together. And so the solution was switching to this setup, really going from a basis of K2 and defining a function basis.toLattice, where we can even use dot notation on, which is just the lattice generated, the lattice defined by the span, the R span of the columns, of the entries of the lattice. And operation basis.twist, which takes a basis and returns a new basis by just multiplying the entries with some scalar multiples or some powers of the uniformizer. And with these two operations, we can state our lemma nicer and rename it to exists reparadist prime. And it reads now as there exists a basis in K2 such that M is the lattice generated by B and L is the lattice generated by this twisting operation applied on B. And the key difference is that now M and L are free variables. So essentially at the beginning of a proof, I can just subst on these two conditions and replace my arbitrary lattices with this explicit representation, and then provide a bunch of API on this toLattice operation and the twist operation, and then just let everything be solved by sim or by some simple rewrites. So just to show how this looks in action, if you want to prove this this distance is invariant under the action of GL2K, the proof really looks like this. So the distance, this is just a statement, the distance of G times M is the distance of G times L, is the distance of M and L. And what do we do? Well, we do in the first step, we just apply our lemma, and you're already in the two referrals here, you observe that what we did was just replacing the M and the L by some explicit b.toLattice and b.twist.toLattice. And now everything is in a standard form. We reduced it to a situation where every lattice is of the form b.toLattice and every other lattice is of the form some twist.toLattice. And now we can just apply a bunch of API on the b.toLattice and the basis.twist and massage this statement into something we can work with. So we just pull in the G and the twist, and now we just have twice the statement distance of some basis.toLattice to some basis.twist.toLattice, and we just apply, we know how to compute these distances, and the goal reduces to this equality, which is true. So really the key here was switching away from submodules of bases of these M's and L's to bases of K2 that generate M and generate L. Because now we could define all of these operations on these bases of K2 and compare these bases of K2 with each other instead of taking bases, lifting them to K2 and comparing the underlying values. Okay, so we have this invariance and we have this distance function that preserves all of these nice properties. So we can say what I already hinted at, two vertices are neighbors if the distance of the vector, if the distance is 1. And the Bruhat-Tits graph is now what we denote by T, is the simple graph formed by the vertices are equivalence classes of lattices, and two vertices are connected by an edge if they are neighbors. And right, this gives us the Bruhat-Tits graph, but of course we want the Bruhat-Tits tree. And so this is eventually the theorem that we want to show. The Bruhat-Tits graph is a tree, and if the residue field K of R is finite, T is regular of degree K plus 1. So, right, so in the case of Q2, we saw that the boring tree, a regular tree of degree 3, because the cardinality of the residue field is precisely 2 plus 1. The residue field is F2, so the degree is 2 plus 1, which is 3. Okay, and so we want to show it's a tree, and in formalization, proving this is quite straightforward. You look up in MathLib, what's the definition of a tree? this is just the copied definition from Mathlib. A tree is a connected and acyclic simple graph. And the first part is relatively easy. The connectedness follows from induction on the distance. What's hard here is the acyclicity. And the acyclicity you prove by relying on the fact that graph theoretical distance agrees with the distance function d. The graph theoretical distance is just the minimal distance between 2 points, the minimal length of a path between 2 points. And a priori, this is unclear whether this graph theoretical distance agrees with the distance function that we've defined before. And somehow the situation, you can understand this in simple situations where all of your lattices are given of the form r plus r and then var pi r plus r and var pi squared r plus r and var pi to the 3 r plus r. And then the distance function is precisely the length. But there's some work to get into this situation. So you prove that by applying the action of GL2K, you can always transform yourself into a situation where it's array like this. And then you can deduce that the graph theoretical distance agrees with distance function. From this, you get acyclicity. And the regularity, for the regularity, you need that the neighbors of a lattice, of a vertex, are in one-to-one correspondence to this projectivization of this two-dimensional vector space L modulo var pi L. And then the cardinality of the projective space of a two-dimensional vector space of a finite field is precisely the cardinality of the field plus 1, which was what was stated in the theorem. Okay, so that's what you get. So goals accomplished. The Bruhat-Tits tree for Q2 is indeed this boring regular tree. And in the minutes I've left, I want to give you a small application of this, of why this was interesting, or how this Bruhat-Tits tree and how this formalization can be used, namely to consider harmonic cochains on the Bruhat-Tits tree. And why are harmonic cochains interesting? So I'll give you an example in a second. Harmonic cochains is some object that you can define on the Bruhat-Tits tree, of which for which it's interesting to consider a cohomology. So eventually you might want to consider the cohomology of some subgroup of SL2QP with coefficients in the harmonic cochains on the Bruhat-Tits tree. And harmonic cochains somehow correspond to harmonic functions. And what are harmonic functions? Harmonic functions are the kernel of the Laplacian. And so we want to get some Laplacian on the Bruhat-Tits tree. And to get this Laplacian, we need some more structure on the tree, namely we need some weight. And this is just, if we have a lattice with some bases, then we say this lattice is even if the additive valuation of the determinant of the matrix spanned by E and F is even. So in other words, we just take every second layer is even and the other one is odd. And this definition doesn't depend on the basis and is invariant under scalar multiplication. So this is indeed gives us a weight function vertices. And so here now the light red ones are even and the dark red ones are odd. And with weights, we now have every second one gets a little -1 and the other ones get a +1. And to define harmonic cochains, we can now define some Laplacian on this. So given a map on the edges of the tree, integer valued map on the edges of the tree, we can associate the map Laplacian of f on the vertices, given by we send the vertices to some sum of the value on the edges times the weight. So what happens is we have some function on the edges given by these numbers on the edges, and we just, at every vertex, we sum the values and multiply it with the weight at this point, and this gives us these dark red values. And, oh, there's this should also be dark red. And so this defines a group homomorphism from the maps on the edges to the maps on the vertices called the Laplacian of T. And the kernel of this are the harmonic cochains on T, which we denote by this HTZ. And the part of the motivation of this formalization was the following theorem, namely the following sequence is exact: harmonic cochains to maps from the edges to maps on the vertices to 0. And wait, this is only fancy wording for saying this map Laplace is surjective. And why is this exact sequence interesting? So this sequence appeared in some research work by Judith with other collaborators, and they used this exact sequence to compute some cohomology groups. And so this was the starting point of the formalization project. We wanted to get this sequence actually done in Lean. And if we now had some more group cohomology tools in Lean and some, for example, some Shapiro lemma, some long exact sequence, we could quite easily start from this and go some more and formalize some part of their paper. Right, so in the end, I don't want to get through the proof, blah, blah, blah. We get that this Laplacian on the Bruhat-Tits tree is surjective, and this proof of this surjectivity of the Laplacian went quite smoothly, and really starting from the tree property, you get this Laplacian in roughly 700 lines of code, which also involves quite a bit of API development that is quite independent of this proof. And yes, so to wrap up, I just want to say the integration into MATLAB, we already pushed some preliminaries into MATLAB. So for example, cardinality of the projective space of a finite field and the definition of its lattice. And what we would like to still upstream is the Cartan decomposition and the tree and the regularity proof. And to conclude, I think constructing the Bruhat-Tits tree was quite a fun combination of algebraic and combinatorial objects, and yeah, really combining these two parts of the library quite closely. And I was surprised that after finding the correct API, working with concrete and explicit objects in Lean was less painful than expected. Somehow working with matrices and bases and always calls for try to work as abstractly as possible and try to not work with explicit objects. But really, as soon as we found the correct API and the correct infrastructure and the correct setup for how to work with these lattices, this explicit handling went rather smoothly. So the project went through a lot of phases, and this is quite visible in the code, that in the beginning, the code was messy and used all of the unprimed lemmas. And then the more the project evolved, the more the usage of the primed lemmas came in. And with it, the smoothening of the API. And for this proof of the surjectivity of the Laplacian, Lean was really a good help in doing these technical induction proofs where Lean helps you to do the bookkeeping and assists you while figuring out the proof. Yeah. And next steps is finish the documentation, make the repository public, and yeah, PR the construction of the tree to MATLAB. Thanks.